Hello everybody. In this video we're going to talk about one new feature in MATLAB that we haven't talked about before, which is the partial differential equation toolbox, or the partial differential equation modeler. And this is one of the nice features in MATLAB that has been released I think in 2017 or maybe 1 year earlier. So it was not there in older versions of MATLAB. And as the name implies, it's used for solving partial differential equations, and this is one feature that is very useful in MATLAB, because we deal with many equations that are partial differential, and sometimes the solution of these kind of equations is not easy, or in general it's not easy. So having this tool is useful, and the nice thing about it, it's that it is a toolbox, so it has a user interface which is kind of relatively friendly, of course, relative to the software or the coding in MATLAB. So there are buttons and there are windows that you can use to put the inputs and stuff. So it's kind of nice feature in MATLAB. So I'm gonna make the first two videos about the partial differential equation toolbox to be focusing more on the basic information and the basic terminology that we need to know and to be aware of, so that we when we see these terminology or these symbols in the software, we don't feel kind of these are like things that we don't know. I'll start with the very basic thing, which is the partial differential equation. So partial differential equations are differential equations, but they have more than one independent variable. So we know that the differential term is dy by dx. If it's dy by dx, then y is the dependent variable because it depends on x, which is the independent variable. So this is dependent and independent variable. So no matter how high the order of the differentiation is, and how many terms we have differentiation or differential terms, as long as we have only one independent variable, this is called an ordinary differential equation. However, if we have more than one independent variable, we call this equation a partial differential equation, and the d is turned to be, or we replace the d with the partial symbol, which is this. And we see these a lot actually, and in many cases we would see the change of temperature with y, or concentration with time. So this is something that is very common, and we will see shortly some examples of the equations that contain partial differential terms. In general, in chemical engineering applications, and I would assume that it's valid for most of the engineering applications, that the differential equations, or the independent variables in the differential equations, are one of two categories. Either it's time, in case of having an unsteady state process, so you have the change of concentration with temperature, with velocity, with pressure, with respect to time. And the second is the space, which is x, y, and z. So these are the two main categories of the independent variables that we deal with. Usually, if we have a partial differential equation, its solution is very tricky. We can do some analytical solutions to partial differential equations, but under very specific cases, and under some constraints, and with the specific boundary conditions. If any of these changes, then we'll not be able to solve them. So that's why we use what we call the numerical solution to solve the partial differential equations. Before we go through the solution, or go talk about the solutions of the equations, we need to kind of take a better idea, or have a better idea about the equations that include partial differentiations. or examples of the partial differential equation. So among the famous equations is the in fluid mechanics, the Navier-Stokes equation, which is a conservation of energy equation. And this is the general form of the equation where Bernoulli equation is considered one of its special cases. So here you would see there is the change of the velocity with respect to time, with respect to x, with respect to y, and with respect to z, and the second derivative of velocity with respect to x, y, and z as well. So this is one type of equations. There is the in heat transfer, the Fourier's second law, which states that the change of temperature with time is function of the second derivative of temperature with respect to x, same for y and same for z. In mass transfer, there is fixed second law, or the continuity equation, which has the so fixed second law is a special case of the continuity equation, but the equation is the change of concentration with time. It has the same change in concentration with x, y, and z as it was in heat transfer. There are many other cases. For instance, if you have an unsteady state plug flow reactor, then it's going to be a partial differential equation. If you have any unsteady state case, then it's most probably going to be a partial differential equation. So this is something that we see a lot and we deal with a lot, and it's important to know how to solve these kind of equations, because if you have this equation and you're not able to solve it, then it's going to be useless. So to understand how the solution goes, we need to kind of revise quickly how we solve the ordinary differential equations, because it's going to be similar in many cases. Of course, with respect to the steps, it's going to be different, but from the main concept, it's almost the same. So for the ordinary differential equations, you can you firstly think of the analytical solution, which is doing the integration as you do in any mathematical class or mathematics class. So you start with the differential equation, you separate the variables if you can, and then you see the integration of each part separately, and then you reach the general form of the equation. So this is the solution of the ordinary differential equation. In many cases, the equation is very complicated. You cannot solve this or integrate this equation, and then you search for another option, which is the numerical solution. And this solution starts with initial and boundary conditions, and then you do some numerical calculations to be able to calculate or solve the problem. And there are some mathematical methods that we use, like Ranjikotta, like Euler. So many methods that are used to do or to solve ordinary differential equations numerically. To understand this numerical solution, let's say that we have a case of a plug flow reactor. So in this case, I have a feed that has concentration of C node, and that is fed to a reactor that starts at a length Z node and ends at the length of ZF. And I want to calculate the concentration at the outlet, which is CF. So this is what we do in ordinary differential equations. What we do is, we know that the concentration changes from here to here. At each point, the concentration changes, and consequently the rate of reaction changes. So this affects the concentration at the next point. So this is how the system is working. So what we do in the numerical solution, we kind of track the concentration at each point in the reactor. So we break this system into small increments. Each one of them is a differential length, and you can put this length with whatever dimension you want. If you want to make it in, let's say if the whole length of the plug flow reactor is 1 meter, you can make it 1 centimeter. You can make the increment 0.5 centimeter. You can make it 1 millimeter. It's up to you. And of course, as you increase or decrease the size of this increment, then the accuracy would be more, because you are getting more points, and this makes the solution more accurate. And by doing this, you assume that this small increment, which is this small disk here, is a homogeneous system. So the concentration and whatever temperature, the pressure, velocity, anything inside this disk is homogeneous, and so you can apply the equation to this small differential length here, or differential thickness here, and then you can calculate the outlet concentration from this first increment by the knowledge of the initial or the boundary condition, which is C node at Z node. And by knowing C1, you can do the same and calculate C2, and you keep going, calculate each concentration from the previous one, and keep going until you reach the final increment or the final disk here, where you can calculate CF minus 1 and consequently calculate CF. In this case, C node and Z node and ZF are the upper and lower limits of integration, and these are the values of the independent variable, and C node here is called the boundary condition, because it is the condition that I know about the boundary, or the end or the start of the integration. So this is how we do the numerical solution in ordinary differential equation. So if you're thinking of this conceptually, it's gonna be the same here and in the partial differential equation. Of course, it's gonna be different because in partial differential equation we have more than one independent variable, but from the basic idea of breaking this whole length into small lengths, and do the calculations on each one of them separately, and then use the output of each one to calculate the or get the output of the other or the following one. It is going to be the same idea. So in partial differential equations, it's going to be the same as we said, and as we said, in partial differential equations, you might have the independent variables to be temperature, time, or space, or both. So you can have it time and x, time and y, time and z, or x and y, x and z, x, y, and z. You can have any combination of independent variables. But of course, the easiest case, or the simplest and more easy to imagine, is the case of 2D geometry in case of steady state. So if you have a 2D geometry, then you have, let's say you have a rectangle and you have change in temperature, change in concentrations in the four barrier or the four boundaries. You have a rectangle with four sides, so for each one of them you have different boundary conditions, you have different concentration, and then you want to see how the concentration will change inside the system. So this is going to be the easiest case. And we will see how we do the solution steps now. But the numerical methods that we use are mainly two numerical methods. One of them is finite element and the other is finite difference. I don't know a lot about these two methods. I know them kind of from the name more than the details, and there are a lot of details included regarding the way of calculations that are done in these methods and how you can calculate each increment from the other, and how or which one of them is more suitable for which systems. There are cases which in which one of them is more suitable than the other, or more accurate than the other. So if you are dealing with any one of these cases, then you have to do your homework. You have to read more and know which one of them is more suitable for your problem. So let's go to Matlab partial differential equation toolbox. So this is what we have here. It is one of the toolboxes here, and as I said earlier, it is kind of user-friendly toolbox that has an easy to deal with interface. Of course, relatively easy, because it's not very friendly, but it's relative to Matlab, it's very friendly. And you'd see here that it provides functions for solving structure mechanics, heat transfer, and general partial differential equations using finite element analysis. So this is the method of calculation that's used in this toolbox. There are more information that are available in the help, so you can check them by yourself if you're interested. Now, if I want to use this partial differential equation toolbox, then you have to define, or you have to follow these steps. First, to define and draw the problem geometry, you have to set the geometry clearly, and define what is the dimensions, how the shape looks like, if it's just a tube, if it's a cylinder, if it's a sphere, whatever the shape that you have to define it clearly, and then define the boundary conditions. And in this case, this is gonna be more detailed than what we used to do, because it's in 2 dimensions, so you might need to define 4 boundary conditions, or more than 1 boundary condition according to the geometry that you have. And then to define the partial differential equation well, so that you can tell how the equation looks like, and this is something that we will discuss in more details later. And then to create the increments of integration. So it's like breaking the plug flow reactor into small increments. It's gonna be something similar to this, which we call meshing, and then to run the solver. Of course, these steps are not clear, and they're not gonna be clear until we open the software and start doing it. But this is like just important to have an idea of these, if it's not a very solid or clear idea, but just to have an idea of the steps that we follow. It's gonna get clearer when we run the solver and see the outputs. I'm gonna come back to this slide after we finish each one of these steps, just to remind you in which step we are working now. Just to compare the partial differential equations and ordinary differential equation, we said that we will define boundary conditions. So if your geometry is rectangular, then you have here 2 boundary conditions at z equals z node, c equals c node, at z equals zf, c equals cf. So this is in the ordinary differential equation. In partial differential equation, you will have similar cases, but for each one of these lines. So you will apply boundary condition here, and here. For the geometry meshing, this is what we do, or what the software does, to break the whole area into small increments, which corresponds to the increments in the plug flow reactor. So in this case, it's not just lines. In this case, it was in 1 dimension, but here we'll have 2 dimensions. So it breaks it into triangles. And this meshing is like a big topic, and the way the triangles are created is important. Sometimes if you have a case where there is like a sharp corner, you will have smaller triangles at this corner to have more accuracy. But anyways, this is something the software does, so we don't need to worry about it. And the output of the solver is, or the toolbox is gonna be something like this. So this is the geometry that we have, and it will give you a colored map with the color code. So this code tells you that if this is concentration, so these light blue color is the concentration of 0. As you get darker in color, it gets to the higher concentration region, and these arrows shows you how the concentration or how the flux is going. So it shows you that the flux is going in these directions. One last thing I want to mention here is the kind of types of problem the software can solve, and this is pretty important actually, which makes our life very easy or more easier when we deal with this software. Is that it's not just giving you x and y and you substitute with the values that you have. It can give you equations of specific systems. So there is the generic system, which is function of any generic variables that can represent anything according to your inputs. But there are equations for structural mechanics, for electrostatics, for magnetism, magnetostatics. I don't know what it is, but this looks like some electricity calculations, AC power, conductive media, DC. So it's kind of structural or civil engineering things and electrical engineering things. But for us as chemical engineers, these two are the 2 important parts, which is the heat transfer and diffusion. So if you choose any one of these, it's gonna give you the equations in terms of the parameters that you know. So it's gonna give you the equation in terms of the mass transfer coefficient or the diffusion coefficient if it's in mass transfer or diffusion. If it's in heat transfer, it's gonna give it to you as heat transfer coefficient. The independent variable or dependent variable is gonna be temperature. So it's gonna be more easy to use and more understandable symbols that you can directly substitute in. So this is gonna be all for this video. In the next video, I'm gonna continue this introduction and talk more about the symbols and the equations that we will see in this software. So I'll see you then, inshallah. Goodbye.